Good morning. Thank you for your flexibility today. Day 3 of chapter 7. I'm at home being dad with a kiddo that has the sniffles and needs to stay home. So, again, thanks for your flexibility. I'm going to put together a little video of all of our problems, warm up problems, and then problems for the day. So, feel free to take out a separate sheet of paper or use a Jamboard or whatever other app you want to use to go through these problems. You could pause the video as I go along and give these problems a shot. This should help you kind of get through whatever we need to get through today. And whenever you're finished, feel free to jump onto anything you have not completed yet, including test corrections and Delta Math and all those good things. But we'll talk about that stuff at some point here through our little video. So first problem of the day, inequality practice. Solve for x, graph your solution on a number line. The first thing I need to do is get x by itself. So I'm going to divide everything. And again, pause the video if you haven't already and check this out on your own. See if you can give it a shot and then compare your work to mine. But I'm going to divide everything by -2. In doing so, I got negative divided by negative is positive. This inequality symbol has to flip and go in the opposite direction whenever I divide or multiply by a negative number. I get x in the middle because -2 over -2 is a giant 1 and then is greater than or equal to. This guy's got to flip -3. I'm not a huge fan of the way that's written. It kind of hurts my brain. It looks backwards to me, so I'm going to rewrite it as -3 is less than or equal to x is less than 2. This means that all of the x's that are between -3 and 2, including, right, equal to -3, make this original, this guy, inequality true. Let's represent that on a number line. Put in some numbers here, -3, -2, -1, 0, 1, 2, 3. I have a closed circle at 3. I get an open circle at 2. And I'm going to shade everything in between here, right? So all of these x values represented on this number line, that's a tough arrow, right? On that number line, they make that original inequality true. It's just a visual representation of those x's. Let's go ahead and clear this and we'll move to our next slide. Two variable inequalities. In fact, we have a system of two variable inequalities. We got to graph this system. I'm going to graph this first one in, let's see, in purple. All right. I first have to graph the line y equals 3x. So I'm going to put a point at 0, 0. That's my y-intercept. Remember, I can kind of think about this as 3x plus 0, right? And then I'm going to go up 1, 2, 3 over 1 to the right. I always run to the right. This is like 3 over 1, x plus 0. And I'm going to put a dash line in because I know that this is just greater than and not equal to. Because it's greater than, I want the y's that are above the line, and I'm going to shade in above the line. Let's change the color here. We'll go to a nice blue. We'll do this one in blue, put a little mark so I know. I now have y is less than or equal to 2. A little bit different here. This is really kind of like 0x plus 2. This time, instead of having a y-intercept that's 0, I have a slope that's 0. So I put a y-intercept in at 2, and I'm not going to rise at all. I'm just going to go straight across. And I get a solid line this time because we have an equal to. And because we're less than, I want to shade in everything below this line. And that kind of makes perfect sense to me because this inequality says everything that works for this is y that's less than or equal to 2. Well, in here are all the y's that are less than, below, or equal to 2. So at the very end of this thing, I'm asked, here's my graph, right? And I got to see, identify any point that is a solution to this system. Any point that is a solution to the system. Well, the solutions live in this now red zone over here, right? Including on this line whenever it's in this purple zone. Let's see what color. I like this lime green. I'm thinking there's a point probably in here that we could pick out. How about the point -1 comma 0? And this is just one point in this zone of solutions, right? That would work for both inequalities. If I put x and y in, it makes both of those statements true. You can test it for yourself. So there's a two variable system. Next, let's go ahead and see what happens when we talk about polygons here. We'll stay lime green. As you work through this particular problem, definitely please get out your Jamboard. and take a look at your Jamboard stuff from last week. This should be something that we're able to kind of buzz through and do at this point. But first, it says consider a regular 15-gon, so we have 15 sides. What is the sum of the interior angles? Well, we want to use the formula n minus 2 times 180 to get there. Right, the number of sides minus 2 times 180. Where does this n minus 2 come from? Well, if we just take a pentagon, for example, last week we took this point up here and we drew these lines and we said, okay, let's make triangles. I know that each triangle, there are 3 of them, has an interior angle sum of 180. 3 180s would give me the interior angle sum of this pentagon. Where does this 3 come from? Well, we investigated to find that it was 2 less than the number of sides. That's where my n minus 2 comes from. So what is the sum of the interior angles for a 15-gon? How about 15 minus 2 times 180, aka 13 times 180. And I just happen to have my trusty calculator nearby. 15 times 180. How about 2,340 degrees total? Yikes. 2,340, that's a lot of degrees in there, right? But that's every one of those 15 angles added together. Number 2 asks, what is the measure of each of those interior angles? Well, if there's 2,340 total degrees and 15 total angles, can I just divide 2,340 by 15? I get that each angle would be 156 degrees. Okay, awesome. So that's the interior angles. What about exterior angles? What is the sum of the exterior angles? Well, we learned that we have to go the full way around the circle and that the sum of the exterior angles is always 360 degrees regardless of how many sides there are. Well, how big is each one? How about 360 divided by 15? So you get 24 degrees. And if you think about that, that makes perfect sense because this interior angle was 156 and the exterior angle was 24. Those angles are supplementary. If I kind of get like a generic shape going on here, if I have an interior angle that I say is 156, this exterior angle that sort of lives out here is 24. They go together to make a straight line, right? They're supplementary angles. They add to be 180 degrees. So that kind of works out perfectly for me as I work through these problems. All right. So chapter 7, where are we now? Well, we've done our compound inequality delta math. We've done our systems of inequalities delta math. We've done our chapter 6 quest corrections. Hopefully you submitted those in Canvas. If you haven't, please get those done today. The end of the class period today will be a great time to get those done. Chapter 7 quest is next Tuesday. We have today and tomorrow together, whether today's kind of virtual, but I should be back in school tomorrow. No big deal. But today we're going to focus on some more polygons. We're going to look at what happens with these polygons, both angles, and then look at area of these guys. So let's dig in and get to work. This is find the missing angles below. Please show all work. So we're going to find C for this one. And again, if you haven't tried this already, jump in and take a time out, take out a piece of paper and see if you can figure this guy out. So for the first one, I know that there are 360 degrees that go all the way around here, right? And there's a 100-degree angle. This is a 90-degree right angle, two 55s. So I know that if I add these together, we have a grand total of 55 plus 55 plus 90 plus 100 would be 300 total degrees right now. 300 total degrees right now, but we're missing this angle C. So what if I just took 360 and subtracted the 300 away? I think that that would give me that this missing angle is 60 degrees. Okay, let's switch colors and switch over to this other problem. Again, stop and pause the video and take a look at this if you haven't done so already or had time. Let's see if we can figure this guy out. Solve for x. Well, I know that I could probably solve for that angle first because these two angles, the 94 and this missing angle that isn't labeled, they're supplementary. So I know that this would be 86 degrees. And then I know that in this triangle, hello triangle, 60 plus 86 plus 2x equals 180. And that's how many degrees, that's the measure of the angles inside a triangle, right? The interior angles of a triangle add to be 180 degrees. So 146 plus 2x equals 180. I can subtract 146 from both sides, and all I'm going to do here is solve for x, right? So 2x equals 34, divide by 2, x equals 17. And if I tried that, if I tested x equals 17, I would get that that whole angle is 34 degrees. And again, the angles in the triangle add to be 180 degrees, and this checks out and makes sense. Notice that there's kind of a cool special extra piece to this, where if you take 60 and 34 and add those together, you get this remote, it's called exterior angle of 94 degrees. That's kind of because of this supplementary relationship that exists here. So kind of a cool little extra side note on that one. All right, a couple angles. We're going to skip this guy. You're welcome to try these out, but for the sake of your time today, we're going to move on and go right to some polygon action with some polygon vocab, and then look at what happens as we find the area of these things. So first you have the center of your polygon, pretty easy enough. You have the radius there in blue, which is just the radius of the circle that your polygon would fit into. You have a central angle in the middle. Imagine that. What an original name, right? Central angle. And you have this height here, and we'll kind of outline this guy. This height right here of the triangle that's created to the center of your polygon. And that's called an apothem. Kind of sounds like you're trying to say opossum, right? Apothem. And the apothem is going to come in handy. It's that distance right there as we find the area of these, or try to find the area of these polygons. So before we do that, it's important to be able to find the the central angle in a shape. For example, here we're asked to find the central angle in the regular hexagon. Well, the central angle, they're all equal to each other. And I think that if we thought about this the whole way around, we get 360 degrees. 360 degrees divided by 1, 2, 3, 4, 5, 6 different angles gives me that each angle is 60 degrees. So I know that this angle, for instance, is 60 degrees. That's going to be helpful here in a second as well. Let's clear this off. And let's go to our next slide. So brainstorm. We want to find the area of the regular pentagon. Okay. So in order to find the area of the regular pentagon, first, again, as I suggest you do with all of these, take a time out and see if you can investigate this for yourself. But I'm thinking the strategy here would be to find the area maybe of that like single triangle and then put the 5 triangles together. So if I can find the area of just one triangle, specifically this triangle, then I'm in business. But there's a problem here because the area of a triangle we know is base times height divided by 2. I don't think I have everything I need for this triangle. I think I have a lovely base of 8 centimeters, but I'm missing this height. So let's pop over here. Let's see if we can find some of the pieces of this. Remember, this existed in this like pentagon here, right? So there are these sides, and we said that this was 8 centimeters. Well, that also means that this side is 4 centimeters, and I have a 90-degree angle right here. What else do I know? Oh, remember, we could find what this central angle is in the pentagon. I know that the central angles altogether were 360, and there were 5 of those triangles. So 360 divided by 5 gives me a central angle here of 72 degrees. If I go one step further and kind of consider just one of these triangles by themselves, maybe we'll get a different color here. And I just consider this triangle that's kind of on the left here. I got a 90-degree angle here. I got a 4 centimeter side here. And I know that this would then be 36 degrees because that's just half of this 72 that I had before. What I really want to know is I want to know this height, right? I want to know that side. We'll label it X. And you have some really nice tools to do this. You have some trig tools where you can find that missing side. So let's set it up. I think that if I were to, again, we'll switch colors here, label these sides. Let's see, I'm using this angle, it's 36. This is the opposite side. This is the adjacent side that makes this the hypotenuse. I don't have any hypotenuse information, but I do have O and A. So if I think about my SOHCAHTOA, I'm not going to use sine or cosine. They both have the hypotenuse, but I think tangent is the way to go. So let's set this up. Let's use tangent to find my missing side. Tangent of 36 equals opposite, 4 over adjacent x. I now have to solve for x. I'm going to multiply both sides by x to get x out of my denominator. So I have x times the tangent of 36 equals 4. Then I need to divide both sides by the tangent of 36. Divide by the tangent of 36. That gets rid of tangent of 36. So that means that x equals, again, let's go to the handy dandy calculator here behind the scenes, and you can do this too. I need to take 4 and divide it by the tangent of 36. I got 5.5055. And I'm going to keep all 4 decimal places in. There's 2 7 after it, so that would be rounded correctly to 4 decimal places. I'm going to keep that in to be as exact as I possibly can. Okay, so that's an important measurement to note. We get 5.5055 as the height. Let's clear this off and go to the next slide. So let's see if we can figure this out now. We found that this height was 5.5055. So the area of my triangle would be 8 times 5.5055 divided by 2. Base times height divided by 2. So times 8 divided by 2. I got the area of the triangle to be 22.022, rounded correctly to 3 decimal places. Area of my triangle is 22.022 centimeters squared, if I want to throw a label on there, but I'm not quite done because I know that I have 5 triangles in my pentagon. 5 triangles in my pentagon means I need to take this area and take 5 times the area of my triangle. So when I do that, times 5, I end up with 110 point, let's see, how about 11 centimeters squared. The area of my pentagon is 110.11 centimeters squared, rounded correctly to, in this case, 2 decimal places. Right? So there you go. If you can find the area of just this triangle, you can multiply it by how many triangles you have, and you're set. Let's see if we can try another example. Okay, again, pause this guy. Give this a shot. I give you the height this time of the triangle, so we're going to have to do a little work. All right, pause this and work through it. And then when you're ready, come back and I'll give you the solution. I have a little extra triangle drawn here to help us, so away we go. I have an octagon here, so I know that my full angle, if I take 360 and I divide that by 8, 360 divided by 8 gives me the full angle of 45 degrees. That means that just one side here is going to be 45 over 2, so 22.5. I'm going to write that in here kind of small, 22.5. It's a little rough. Let's try that one more time. I know that one side would be 22.5. I know that this side is 10 centimeters. I need to find x. So away we go. Tangent, because I have my opposite and adjacent sides. Tangent of 22.5 equals opposite x over adjacent 10. I'm going to multiply both sides by 10. If I multiply, it's supposed to be a 10. If I multiply both sides by 10, I get rid of this. I have x equals, let's go again to the calculator. I have the tangent of 22.5 times 10. Oh, something happened on my calculator. Let me try that again. Okay, there we go. I got 4.14, corrected 2 decimal places. That's my x distance. Now be careful. That means my base all the way across of my triangle is really that doubled. It's really 8.28 centimeters across. Now I need to find the area of my triangle. The area of my triangle is base times height divided by 2. So the area of my triangle, little triangle there, is base 8.28 times 10 divided by 2. Let's go to the calculator. 8.28 times 10 divided by 2 is 41.4 centimeters squared. That is the area of one triangle. But I really, in my octagon, have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 triangles in my octagon with 8 sides. So here we go. 41.4. I'm going to come up to the top. 41.4 times 8 triangles gives me a grand total area of 331.2 centimeters squared as the area of my regular octagon, right? Talked about regular last time, meaning that all the sides are the same length and all the angles are the same, which allows us to go through this process. All right. So right now I'm going to erase this guy. If you need it again, you can always go back and check out the video again. Right? Power of rewinding. Right now I'd add this to your toolkit. I would go back to the previous slide and I would take all the work that you had for this guy and I'd give that a screenshot. You can give mine a screenshot if you want to, and I'd add that to your Jamboard. And I'd also take these steps and I'd add these steps in, right? Because this is what we went through here. We found the measure of the central angle. We broke one of the triangles in half. We solved for the base and the height, whichever one we didn't have. We found the area of the triangle, and then we multiplied by the number of triangles. So we multiplied by 5 for the pentagon, 8 for the octagon. It's based on the number of sides. So I would pause this right now. I'd add this to your toolkit for area of a polygon, and I'd go from there, right? We're going to do some more practice with these, but this should certainly help get you started with the area of a polygon. All right, I have one more for you to try. You can go ahead and give this a shot again. Pause and make sure that you're all set. This one actually is pretty straightforward because it doesn't have you do any of the angle work. It really makes this really nice because and again, you can pause this, but I'm going to work through it. This is 14.4, and it gives you this base is 13.9. So kind of take some of the trig work out of this. Make sure you have the right idea. So the bottom line is we're going to take this triangle that exists here, and we're going to find the area of this triangle. The area of the triangle would be 14.4 times 13.9 divided by 2. And I got to hit the calculator again because that's a little bit too much decimal action even for this guy. And the area of my triangle, it's supposed to be the area of a little triangle there, right, is 100.08. And then I have 8 triangles in my octagon. It's an octagon again. So I need to take my final area is going to be 8 times the area of one triangle. So when I multiply by 8, I end up with a grand total of 800.64. And there are no units given here, so I'm just going to label this as units squared to denote that this is in fact an area. Okay, so there's another example for you. This one's a little bit easier because it takes the trig out of it, takes some of that angle measurement out, gives you the height and the base, but I just wanted to give you one more example to make sure you had the right idea as we were going through these problems since they're kind of new. So what's next? Hopefully I'll be back in school tomorrow and everything will be right in the world. We're going to talk about circles. We'll go over some things. We'll answer any questions that you have, and then we're going to do a crash course in everything circles to kind of finish up chapter 7. We'll talk area, we'll talk sectors, we'll talk circumference, we'll talk arc length, we'll talk arc measure, and that will set you up for your virtual days next week, Monday, Tuesday, and Wednesday. That is circles, circles, and more circles. When you come back, Thursday next week, chapter 7 review on Thursday, and a chapter 7 quest on Friday. Hopefully this worked for you. Hopefully you're able to follow along and try some of the problems on your own. If you're at this point in the video, that means you've finished. So please feel free to jump into any Delta Math that you did not finish this week. Please feel free to check out any of your test corrections that you did not complete. If you have questions, please shoot me an email and let me know. Stay in communication here. And like I said, hopefully we will see you tomorrow. So thank you so much and have a wonderful day.